Good morning, educators. Today we are going to present you our project, an investigation on auto-regenerated hydrogen carbonate promoted by synthesized metal ion adopted iron free oxide induced photocatalytic water splitting for hydrogen production. Hydrogen has a strategic importance for the resources for clean energy in the future. However, the hydrogen production method nowadays is either dangerous or expensive. For example, steam methane reformation. Therefore, we are going to investigate this project to find a more efficient way to produce hydrogen.
Now let me introduce you our principles. The first one is the band gap theory. Since iron peroxide itself is a semiconductor, its conduction band as well as valence band is separated by a band gap. So when photons containing energy equal to or slightly larger than the band gap of the photocatalyst reach them, the electron in the valence band will promote to the conduction band, leaving a positively charged hole in the valence band. The electron in the conduction band will reduce hydrogen ion to hydrogen gas, while the hole left in the valence band will oxidize hydroxide ion to hydroxyl radicals, which with the aid of another hole will oxidize glycerol to produce hydrogen gas. After photoexcitation, the electron in the conduction band may fall back to the valence band and recombine with the hole, which is called a relaxation. According to literature, the recombination rate in iron peroxide is actually very high. So in order to solve this problem, as well as to enhance its performance, we have investigated three methods in total. The first one is metal ion doping. Since the metal ion doping will provide three extra ways for electron promotion. The first one is from the valence band of iron peroxide to the conduction band of the metal ions, and it will promote from the valence band of the metal ions to its conduction band or to the conduction band of iron peroxide directly. Besides, we can reduce the recombination rate of iron peroxide through electron trapping. After photoexcitation, the electron may fall back to the conduction band of metal ions instead of falling back to the valence band again, so the hole will not be filled up and the recombination rate can be reduced. And the second way that we have tried is dye sensitization. Since the band gap of the dyes that we have chosen are relatively narrower than that of iron peroxide, less energy will be required for photoexcitation. So the electron will promote from its valence band to the conduction band and transfer from its conduction band to the conduction band of iron peroxide through a process called intersystem crossing. So a broader range of visible light can be utilized for photoexcitation and further hydrogen production. And the third way we have tried is the addition of hydrogen carbonate ion as well as carbonate ion. And the hydrogen carbonate ion, owing to its electron-rich nature, it can provide electron to fill up the hole. So the electron in the conduction band can no longer recombine with it, and it can only reduce hydrogen ion to hydrogen gas. Therefore, the recombination rate as well as the currents will be reduced. And the hydrogen carbonate will be oxidized to form carbon dioxide, where carbon dioxide will react with hydroxide ion in water to form back hydrogen carbonate ion as well as carbonate ion. So this is actually an auto-regeneration process. And this one is a reaction by which hydrogen carbonate ion as well as carbonate ion will decompose by the hole to form carbon dioxide.
And as you can see, this is our general setup. The O-ring lamp here is to provide light sources for the setup. And since the iron free oxide is insoluble in water, we would like to use a stirrer and a stirrer plate to ensure that homogeneous light source is kept. And we will use, to prevent the light sources from escaping from the setup, we will use a box wrapped with aluminum foil to cover the whole setup. And the hydrogen producer, we will use the pressure sensor to measure the pressure, and with the aid of the ideal gas law, we will measure the volume of hydrogen producer. And there are actually 7 factors in this setup that will affect the hydrogen produced, the amount of hydrogen produced, and the ultimate results will be here.
So in the first experiment, we would like to find out the best photocatalyst and its optimal mass. And we find out that 0.8 gram of iron peroxide with, in a condition of 30 ml of water as well as glycerol has the best performance among the 4 photocatalysts that we've chosen. And the reason why iron peroxide is The reason why iron peroxide is the best photocatalyst, the reason that the barrier of the iron peroxide is actually narrower than that of the rest of the photocatalysts. So less energy will be required for photocatalysis, and iron peroxide can actually utilize visible light for photocatalysis and burn halogen production. And according to the absorption spectrum, it has a wide absorption spectrum as well as it has a very high absorption peak. And it can also absorb up to 500 nanometers of light, which is part of visible light. So we reason that this is we think that this is the reason why iron peroxide is better than the rest of the catalysts. And in the second experiment, we have tried to find out the best volume ratio of water to glycerol. And we have found out that 9:1 is actually the best volume ratio between water and glycerol. And in this experiment, we have tried to find out the best metal iron doped iron peroxide in different calcination temperature. And we found out that zinc iron doped iron peroxide calcin at 600 degrees Celsius shows the best result. And we reason that the zinc iron doped iron peroxide will have a very significant redshift in its iron peroxide absorption spectrum, and it narrows its bandgap by a significant amount. Therefore, less energy will be required for excitation, and a broader range of visible light can be also utilized. So it will be more efficient for zinc iron doped iron peroxide to be used in halogen production. And in this experiment, we have tried to find out the best sensitizer, and we found out that chlorophyll among the synthetic dyes as well as natural dyes are the best photocatalysts. And we reason that chlorophyll can utilize up to 600 as well as 700 nanometers of visible light, as well as 300 to 500. So it's actually a very, very broad range of visible light, and it will be more efficient to use chlorophyll. And these are the results of synthetic dyes. And in this experiment, we would like to find out the best reaction promoter. And we found out that in general, 1 molar of sodium halogen carbonate, 9 ml of 1 molar sodium halogen carbonate shows the best result. And we reason that and we cannot find out the reason why halogen carbonate is better than carbonate ion. And in this experiment, we would like to find out the best pH effect of zinc iron doped iron peroxide, and we found out that pH 14 shows the best result. And we reason that according to the point of zero charge, and when the pH is higher than 6, more halogen ion will be attached on the surface of iron peroxide. So its halogen attracting potential will be higher. So halogen ion will have a higher chance to be reduced to form halogen gas, and therefore it will have a better performance. And in this experiment, we would like to find out the best pH on chlorophyll sensitized zinc iron doped iron peroxide, and we found that pH 10 is the best. And in the alkaline condition, the magnesium group of iron, in the acidic condition, the magnesium group in the chlorophyll is actually missing. So its absorbance will be reduced, and some of its red part of its absorption spectrum will disappear. So it will affect its performance. Under pH 14, an ester group in the iron group in chlorophyll is disappeared. So its absorption spectrum is affected, and its performance is affected. And in comparison, we found that our method only requires the room temperature as well as room pressure. In comparison to the steam methane reformation, which is the most common way to produce halogen gas nowadays, it requires a very high pressure as well as temperature. So its cost is very high, and then it has a very, very high risk. And besides, our method of halogen production is renewable, as we use solar energy, as well as iron peroxide itself is a photocatalyst, so it will not decompose during the process. Besides, water is very, very abundant, as well as the glycerol can be extracted from coconut oil. So our method will be more environmentally friendly, as well as it is renewable.
So in conclusion, we found that the best catalyst is 0.7 gram zinc doped iron peroxide contained at 600 degrees Celsius. And the best sanitizer is 9 ml of 0.3 molar chlorophyll. And the best water to glycerol ratio is 54 ml to 6 ml. And the best reaction promoter is 9 ml of 1 molar sodium hydrogen carbonate. And in our process, in our project, we are able to convert waste oil to green energy, and we are able to utilize the auto-regeneration of hydrogen carbonate and carbonate. Also, we are able to exert rust as photocatalysts. And also in our project, our one core system is carried out, and we are able to utilize 43% of visible light. Therefore, high mobility, high efficiency, and safe hydrogen pollution method is investigated. However, it is believed that many possible improvements can be made. For example, we can investigate on different solutions to extract chlorophyll, and we can investigate on the optimum operation temperature, and also we can investigate on using other methods to increase its efficiency, such as the metal ion co-doping. This is the end of our presentation. Thank you.